So, one option, and I don't know if we highlight this enough, or I don't know, you guys recognize the power of your graphing calculators, but one option you have anytime you come across any equation and you want to solve this equation, one option you can have if you have your graphing calculator available is to use your graphing calculator, right? To solve any equation you ever come across, at least in a single variable. Take the left-hand side, put it in y1, take the right-hand side, put it in y2, and see where these two things intersect. Okay, that's one option. You could just use your graphing calculator, type it in the left hand, type it in the right hand, and see where they intersect. This could get out of control here, though, because we are going to be graphing 8 to the x. But let's just see. So 8 to the x, and then 2 to the 6. Yeah, it's going to be a little bit crazy. Okay, so I graph it. You can see there's my exponential curve there. It's, super steep, super sharp increase because it's, 8 to the x there. So we're multiplying by 8 each time. I'll go up by 1. So let's see here. It looks like I need to adjust my window, especially since 2 to the 6th I know is going to be, 64. So it looks like I need to go up higher here. So I'll adjust my y max and go to like 70 maybe. Okay, so there's the curve. And there's the other side of my equation. And so I can just hit second trace, go to intersect. Okay, so I'm on my first curve right here, you can see. I'm on my second curve right here. And the guess is important, as I told before maybe, or if I haven't told you before, the guess is important because sometimes your curves intersect in more than one spot. Okay? So you want to move that guess cursor close to the place where it actually intersects and hit enter. And then you can see there's your solution. X is 2. Okay, x equals 2 would make this equation true. Okay, use our graphing calculators there. Of course, there's other things you could do here. For example, we know that to the 6th is 64, right? We can actually calculate that out. And so we see something like this. Again, we can just use mental math. Oh, 8 to what power is 64? Well, it's just 8 to the 2. 8 to the 2. So x is 2, right? It's got to be. That's another way right there. Okay, just using kind of mental math. And then one other strategy we can use here. And we've already been kind of using this, but here we're officially kind of going over it, is to rewrite the equation in terms of the same base. Okay. So in other words, that's like taking that 8 to the x and the 2 to the 6th. Okay, starting again there. Right, 8 we know is 2 to the 3rd. So you can rewrite that 8 as 2 to the 3rd to the x equals 2 to the 6th. Ooh. And of course, when we have a power 3 raised to another power x, how do we simplify those powers? What do we do with them? 2 to the 3 to the x, what do we do? Multiply, so it's 2 to the 3x equals 2 to the 6th. Okay, and again, this is where we've seen that at this point, right, we have the same base, and the two values have to be equal, and so that means 3x just has to equal 6, and so then we divide both sides by 3, and x is 2. Okay. 2 does not have to be your common base here in this case. For example, 64, you can rewrite that as 8 to the 2. So you'd have 8 to the x equals 8 to the 2, and so then x would have to be 2 that way as well. Okay. So you kind of have some freedom about, what base you use. I'm going to recommend that you try and always reduce things down to like their lowest base, I would say. So, like while 64 can be reduced down to 8, sometimes publishers reduce it down, to their like the lowest base of 2. But it's kind of whatever works for you there. Okay. Let's try another one. Again, same directions. We're just going to solve for x. Alright, and let's say I've got 7 to the 3rd to the x over 49 equals 1. What might be a good common base here? What might be a good common base to get here? Yep. 7, yeah, exactly, okay. So in fact, the numerator is already we can just rewrite that as 7 to the 3x. 49 will be 7 squared. And then, how do you write 1 as a power of 7? 7 to the 0, or 7, yeah, to the nothing there, right? 7 to the 0 is 1. Now that makes it nice. Okay. So let's see here. We have division. And since we're dividing the same base, what do we do with our exponents? Subtract them. That's right. So it's 7 to the 3x minus 2 equals 7 to the 0. Isn't it interesting, by the way, and that when we talk about exponents, when we have division outside two numbers with the same base, it becomes subtraction kind of inside the exponent. Whereas with logarithms, we have division inside the two logarithms, and it becomes subtraction outside the two logarithms, right? Separating two things. Almost like, there's a relationship there. But anyway. 7 to the 3x minus 2 equals 7 to the 0. Same base. They're supposed to be equal, so we just set the powers equal to one another here. And so you get x equals 2/3. And of course, you can check this, right? You can plug that 2/3 back in up there and see that you get that. This actually wouldn't be too bad to check. I mean, you could check that mentally. Okay? So here, you guys try. Actually, I should ask any questions. No. Eager to try one on your own? Gotcha. Solve for x. Okay, I'm going to give you 2. First one, 27 to the x equals the cube root of 81. And then number 2, 3 times 2 to the x equals 42. Okay? And you can use any method you want there to solve those. Any method you want to solve those there. Okay? Use any method that you want to solve there. Any of the stuff we just talked about. It'd be nice if it was. Yep, that's right so far. Great, fine. So keep working from here. So what is the square root? What is that as an exponent? Oh, it's a cube root anyway, but yeah, what is that as an exponent? 1/3. So it'll be 3 to the 1/3. Yep. For both of them? Right. Retype in the first one for me so I can see what you typed in. Okay. Please. So I don't want to type it in. I'm just practicing mouth safety here. No, you don't need to. 81 is fine. It is or. I mean, you can figure it out, right? So let's just think 3 times 30 because it's 3x now that would be 27. Oh my god. What did you get? So these, we can't quite multiply these together because this has 2 to the x, and this is just 3. So that would yield that, and also then it's this is not 6 times the x, it's 6 to the x, right? So it's 6 to the 7th power. We multiply 6 by itself 7 times, but now it's 42, right? It's much bigger. So consider using your calculator. No, the first one's good there. Okay, that's looking good. And that's looking, yep. Question? Yes, Kenny, right there. Oh, James, I'll be right there. All right. Oh, that is correct. That is correct. What I'd like to do is try to have you calculate.
I just like skip over the ones that are 30 and 60.
And this one you have to. So when you see this, like 114, you can kind of like take the calculator. The key here, and this is what 27 and 81 are both powers of the same number. They're both powers of 3, right? Do you recognize that? If 27 is 3 third, 81 is 2. Yeah. So I mean, the thing is, like, maybe 81, you're like, oh, that's kind of larger. I already know what that's the power of. But 27, you recognize that's 3 to the third, right? Then, well, then I gotta be able to write 81 as the power of 3. Well, I can't write 81 as the power of 3. I'm stuck anyway. Like, in order to solve these, most of the time you need a common base. Yes, it does. That's the exponent. So we're gonna have 3 to the 4th to the 1/3. So that's 3 to the 4th, and then to the 1/3.
Oh my god.
Perfect.
Yep.
So what I like
No,
to do
don't worry
You
about
got
it.
it now?
I didn't realize what they were putting.
3 to the 4th number. Now, when you power base down, you multiply. So really, it's like 3 to the 4th. Because. Okay, folks. Let's take a look at this. Number 1 is 4/9, and number 2 is 3.807. Approximately.
Was the only way to solve number 2 with the calculator?
You can do that in your head?
No, I could not.
Well, I guess if you need to use a calculator, you can. No, yeah, that's the only way to do it is use a calculator. Yes, absolutely. Yeah, number 2, you can only do it with the calculator, and that's why I said you can use any method that we just talked about that you want there. Okay, I wasn't trying to be tricky, but what's important to recognize here, right, is our own limitations, right? Not only being able to recognize when we can do a problem, but also recognize when we can't do it and we have to go to technology, right? Number 2, the point was 2. So you may have like looked at number 2 and maybe just from the very get-go you're like, I have no idea what to do. You know, with this, I said, okay, we have a 3 out front, so we could divide both sides by 3 to kind of get that 2 to the x by itself equals 14. The problem at that point, right, is that 14 is no power of 2, or at least no nice power of 2. And so we can't solve this using, you know, paper and pencil. We have to go to technology or some other method. Of course, we could, you know, estimate it, right? Anyone, you know, you guys here are capable of estimating it. 2 to the 3rd would give us 8. 2 to the 4th is 16. So it's somewhere between, you know, 3 and 4. Closer to the 4 because it's closer to that 16. But that's about the best we're going to do, right? So there's the idea. 1 could be done completely without a calculator. Important to recognize that the, you know, the common base there, right? 81 can be rewritten both as 9 squared, right? It can be written as 9 squared, but of course 27 is not an easy power of 9, and so we wouldn't want to use a common base of 9. But both of these are powers of 3, and so then you rewrite it to 3. All right. And again, once you recognize that, you know, like for example, 27 is really only a power of 3, once you recognize, okay, 27 is a power of 3, if you can't write 81 as or I guess the next step is to then try and rewrite that 81 as a power of 3 too, right? Once you figure out one of the common bases here, then you know the other one's hopefully got to be a power of that base too. Okay. Any other questions on 1 or 2? Tomorrow's quiz? Could be. Could be. Why do you ask? Yeah, could be. Yep. I believe it will be non-calculator though, so probably not something like that, because otherwise, you know, that'd be ridiculous. Okay, so. But yes, it could be on tomorrow's quiz. Yes. All right. Let's do a few more here. Okay, so. All right. And in fact, I'd like to go back and talk about this guy right here, number 2. So, like, how do we? What else can we do here when we have something like 2x equals 14, right? Because really, to get x by itself here, right, to solve for x, right, which is what you normally want to do when we solve an equation, right? Here we solve the equation, got x by itself. Here we got x by itself, but we had to use a calculator, right, to get the actual like or a value. How can we get like a more precise value here, though? Okay. Well, what do we have that allows us to take something out of an exponent like that? A logarithm, right? And so if we take the log of both sides, what base logarithm should we use? Well, it turns out you can use any logarithm that you want, okay? You might be tempted to say, oh, Mr. Wade, we should use log base 2 because this is 2 to the x, and we should use log base 2 because, you know, that's our base there. But really, any logarithm will do here. Let me just show you that. If I take, for example, the natural log of both sides here, okay, and again, when you take the natural log, it's of the entire side. So it's the natural log of the left-hand side equals the natural log of the right-hand side. Okay, the entire side. Just like when you square root. You can't pick and choose where you square root. It's the natural log of the whole side equals the natural log of the whole side there. Now, since we took that natural log, that x and the exponent can come down out front. So we have the x times the natural log of 2 equals natural log of 14. And what's our final step here to finish solving for x? Yeah, Dylan? Exactly right. Divide both sides by the natural log of 2. And so you get x equals, as Dylan said, the natural log of 14 over the natural log of 2. Okay, if you don't like natural log, you could use log, you know, like log base 10, the common log there. Okay. It's up to you. What if we use log base 2 there? What if we use log base 2? Well, let me just show you. Log base 2 of 2 to the x equals log base 2 of 14. Okay. Log base 2 of 2 to the x. What is this asking? Well, remember, log base 2 of 2 to the x, that's saying 2 to what power gives us 2 to the x? So what does that just simplify to be? X, just x, right? 2 to what power gives us 2 to the x? Well, it's got to be x. So that cancels it all out just to x, and then we have equals log base 2 of 14. So log base 2 of 14 is the same thing as the natural log of 14 over the natural log of 2? Well, let's see here. Again, I have that nice button on my calculator where I can do, oops, not here, on the home screen, okay, where I can actually do like a log, you know, with the actual base address. I can do log base 2 of 14, and there's that, and then natural log of 14 divided by the natural log of 2, and it's the same thing. You guys recognize this here? Does anyone recognize what is? Change of base. Change of base, right? Natural log of the big number divided by natural log of the small number. It's just a change of base. That's all it is. It ends up being a change of base. Instead of log base 2 of 14, we wrote this equivalently in a changed base e here. Okay? You do the same thing. Log of 14 divided by log of 2. Same thing. Log base 10, log base 10. So that's how we can precisely solve these, right, without the aid of a calculator, is using those logarithms. All right, so let's try another one here. And let's solve for t instead. Okay, so we'll do 6 times 2 to the t plus 5 plus 4 equals 11. Should we start trying to use logarithms at this point? Should I just go ahead and just take the log of both sides at this point? No, we don't want to do that yet, okay? You want to isolate that exponential. So in other words, the exponential, what's that? That's the thing that's being raised to the power with the variable in it, right? So this 2 to the t plus 5, we want to isolate that. So in order to do that, we want to get it by itself, right? So we'll subtract 4 from both sides, for example. And then we should, what should be our next step? Divide both sides by 6. Okay. And now we finally get to the situation where it's like, all right, we've got 2 to the t plus 5. We've got to get that t out of the x star. Okay, and again, it's up to you what logarithm you want to use. If you want to use log base 2, if you want to use log base 10, if you want to use natural log, that is log base e, use log 15, log 16, whatever you want. Okay, I'm going to use, I'll just use log, the common log here. So I'll take the log of both sides. So we have t plus 5, that quantity, times the log of 2 equals the log of 7/6. And divide log of 2 over. Okay, and then we'll subtract 5 from both sides. Whoops, there we go. So now we have a precise value. Precisely, the value of t is log of 7/6 over log 2 minus 5. But of course, you can go to our graphing calculators and get a approximate decimal value there. Make sure that you use parentheses, right? Close the parentheses around the 7/6 before you divide by log of 2. And you can just subtract the 5 too. And you get negative 4.778, it looks like. And of course, you can check this in your graphing calculator, right? You can use that negative 4.778. I can do 6 times 2 to the negative 4.778 plus 5 plus 4. You'll notice I get 10.998. Is that okay? We didn't get 11 there. Is it okay that I didn't get 11? Yes, why? Why is it okay that I didn't get 11 there? Yeah, done? We rounded the t value there, okay? We rounded the t value, so we'd expect then, because that's rounded at the, we won't get precise. We got awfully close, right? Pretty close there. 10.998 is pretty darn close. So we'd expect that if we did, the exact value, which, by the way, you can do. If you, again, there's my actual value. If I go, let's see, I think if I do this and hit enter, okay, if there's like a way you can actually store this. So this is like, even though your calculator is kind of rounding it because it doesn't list, all the decimals here, you can actually store this exact value in your calculator. If you guys never knew this, right, you can press this little STO button, short for store, I'm sure. Okay, it brings up your answer, and then it has a little arrow, and then you can type in the variable x. So it's going to store that answer in for x. And so now anytime I press x, it's going to use that on the home screen here. If you go to graph stuff with x, it's still just the variable x. But now on my home screen, anytime I use x, it'll be that value. So then I could do 6 times 2 to the x plus 5 plus 4, and you'll see I get precisely 11. Okay, precisely. So that's nice. Okay. If you don't want to round and potentially be off. All right. Questions on any of that? I got one more for you here, and then we're done. Okay. Okay, and this is a bit of a next one here is a bit of a different style. Okay, and I kind of wish I didn't have to use, but oh well. Oops, solve that. Okay. So this is a bit of this is a bit of a different kind of problem than what we did earlier here. We still have our exponent x. Our exponent still has x, right? Our variable here is up in the exponent. All right. The problem is, though, if I try and isolate these, I really can't, because this is e to the 2x, whereas this is just e to the x. So I could subtract the 2 over here. Okay. I get something like that. But now if I take the natural log, if I try and or if I take the log of each side, or the natural log might be a good idea, because remember, natural log is log base c. If I try to take the natural log here, I have to take the natural log of the entire quantity. And there's no way that we can split up subtraction inside a natural log. And so we won't be able to do anything with those x's. Okay, we can't split it up, right? You can't just pull that x out front because it's got the subtraction in there. We could, if we don't want to do it that way, we could say, okay, well, e to the 2x minus 3e to the x equals negative 2. We can factor an e to the x out, leaving behind e to the x minus 3. But the problem with this is that, again, we have two things that are multiplying to negative 2, and we can't, again, break that up, right? If it was equal to 0, that'd be perfect, because then we could just set each factor equal to 0, right? We'd use the zero product property, but negative 2, can't really do anything with that either. So we can't factor. I mean, we can factor like that, but it's not helpful. It's not helpful. So, what do we do in a situation like this? Well, anyone have any ideas? Can anyone see it? Okay, yeah, Alyssa?
Do you not bring the 2 over?
So we don't want to bring the 2 over. We want to leave the 2 where it is. That's right. Okay, so let me rewrite it one more time here while I'm ugly handwriting. Let me show you something here. We've got e to the 2x, which is really e to the x squared, minus 3 times e to the x plus 2 equals 0. Or in other words, we have something squared minus 3 times that same something plus 2 equals 0. And so this thing factors like a quadratic, or we can factor it like a quadratic. Okay? We can take that something and do minus 2 and that same something and then minus 1. And the something here is, of course, e to the x. Okay, it factors like a quadratic would. And now we have two things that multiply to make 0. We can set each one of those two things equal to 0. We can add 2 to both sides here, and add 1 to both sides. And then finally, to solve for x here, what can we do now? How can we get that x out of the exponent now? What do we use? A log, right? I'm going to use natural log. I'll just take the natural log of each side here. Okay, and so the natural log of e to the x will be just x equals the natural log of 2. Natural log of e to the x is just x equals the natural log of 1. Okay. So we have x equals natural log of 2, and natural log of 1 is what? 0. So x is equal to 0 is another one. Okay? So there are your two solutions. Natural log of 2 and natural log of 1, or 0. Okay? Question on any of that? Okay. So there's another one of those, like, you know, a sneaky quadratic, right? A sneaky quadratic that shows up unexpectedly. There's something else I feel like I wanted to say. Oh, okay. I'll think about it some more. I can't remember. Okay. Any questions on any of that? No? All right. So let me get you guys started on your assignment. I think you'll see one of those at least in your homework. All righty. Page 224. Wait a minute. Not page 224. Page 251. Sorry about that. Page 251. Numbers 30 to 42. 51 to 63, and again, that's every third, or multiples of 3, if you want to think of it that way, right? Every third or multiples of 3. And then also, don't forget to do 68 and 132. It's pretty crazy. So 30 to 42, 51 to 63, and then 68 and 132. All right.